as well. Okay, so this is the MRI safety training for MRI personnel. So after the training, supposedly you are not only comfortable working around the MRI area, you will also be able to ensure some visitors or your participant for your safety around the MRI area. I'm going to go over a few sections. The first is the basics of MRI, and then I'm going to go through. Okay, sorry. So I'm going to talk briefly about components in MRI, and then hazards in MRIs, as well as MRI safety guidelines at CTRIM and some emergency protocols. Okay. First of all, basics of MRI. So this is all the nuclear spins, and this is basic chemistry probably. And you can see all these different elements, and anything in yellow or orange here are things that can potentially make MRI signals. So other than protons, you can have carbon, sodium, phosphorus, who all can give MRI signals. But we are going to focus on proton now, with a geomagnetic ratio of 42.57 megahertz per Tesla. And it's very, very naturally abundant. All your human body are made from protons. So when you put all this, when your human body are outside, you have all, without the MRI field, you have all these protons are randomly oriented. But as soon as you apply an external magnetic field, all these protons will listen to this magnetic field and will be aligned. They will either be aligned in the direction that's parallel to the magnetic field, but all of these things are going to be a little proton. They're going to be spinning. Or they will be anti-parallel to your applied magnetic field, but they are also going to be spinning. And then all these little spins are going to spin at a certain frequency, which is called a Lamo frequency. So remember, we talked a little bit about the geomagnetic ratio for protons, which is 42.57 megahertz per Tesla. So the spins in your human body are also going to be spinning at a slightly different frequency at different magnetic strengths. So for example, at 1 Tesla, it's going to be spinning at 43 megahertz. At 1.5 Tesla, it's going to be 64 megahertz. And at 3 Tesla, it's going to be 128 megahertz. Okay. So if you think in terms of a quantum mechanics approach, and I promise I won't go too deep in the math. So these parallel or anti-parallel spins are actually having a slightly different magnetic field energy level, depending on if they are positive 1/2 or negative 1/2. So these anti-parallel spins are going to have a slightly higher energy than these parallel spins. Why does it matter? Well, it matters a little bit. So if at 0 Tesla, which is no magnetic field, you have 2 million protons or 2 million spins. At 0.5 Tesla, you have these 3 excess protons that will be spinning at the lower energy state than the higher energy state. At 1 Tesla, 6 excess protons, and at 1.5 Tesla, 9 excess protons. And there's a wider and wider energy difference between these 2 groups of spins. And then your total magnetization, where your MI signal is being produced, does not depending on your 2 million protons, but on this a little bit of excess protons. So that's tiny, right? But it's fine because in 1 millimeter cube tissue, you actually have a lot of excess protons. You have 10 to the 13 power of excess protons. So you still have a lot of protons to give you signals. And this is so-called proton density, a signal weighting in MI. But it also explains why when you go to a higher field strength, you get higher signal to noise ratio, purely because you get more excess protons to give your MI signals. And other than proton density, you have some other MI signal properties. One is called T1, which is the spin lattice relaxation. So it's a relaxation time. And you can see different tissues will have slightly different recovery time after they are being excited. And this is called a T1 property. And when you see image that's T1 weighted, typically white matter appears whiter, gray matter appears darker. So this is the T1 weighting that you are looking for. There's another thing called T2 weighted sequences. So T2 time is characterizing these spin-spin interactions after the spins are getting excited. So it's a different relaxation or the decay, so-called, because it starts from a strong signal, goes to 0 after excitation. And again, you have different tissue type will have different T2 values. And here you can see T1 and the T2, like gray and white matters, having similar T2 property, but you can see the CSF is extremely bright, which means that T2 of the CSF is actually drastically different than your T1 and than your gray and white matter tissues. And of course, in your MI, the beauty of MI is you have a lot of signal contrast to play with, right? So you have a T1 weighting, your T2 weighting, and you can make a whole range of imaging contrast within there, which is shown and on the little graph here. And again, we're not going to go to the details, but just know that by manipulating your imaging weightings, you can get all kinds of different contrast. Okay, quickly, we're going to go to the components in MRI. So 3 main components in MRI. Magnet, the main magnetic field, which is actually the most expensive component in MRI. And a little quote is, you go to a higher field strength from 1.5 Tesla to a 3 Tesla scanner, typically your cost doubles because the main cost is actually the main magnetic field. So the main magnetic field, it's useful to get all your spins, right, to be aligned, to be ready for your MRI imaging. So you can see that the majority here is your main magnetic field. So can you see my arrows? Yes, no? You can speak?
Yes, we can.
Okay, great. Okay, so if you can see my arrows, I'll just move around. So you can see that the main housing is actually to house this super heavy magnetic field, main magnet. And then you have your radio frequency coils, and which is typically the closest to the person's body, because you want least the most closest approximation to the person. And then sandwiched between your radio frequency coil and your main magnet, it's typically your gradient coils, which you can see it's color-coded by XYZ gradient. And these are the whole thing that's sandwiched in between. That's mainly for spatial localization. And let's go into each component. So the main magnetic can have two kinds of constructions. You can have this type A, which is an L core magnet. It's typically using a superconducting electricities. Whilst from the electricity, you make your magnetic field. And it's typically horizontal. And you can see that with this L core magnet, other than in the middle of the scanner that you have your magnetic field, you also have a lot of fringe field. We call it the fringe field that extends beyond to your magnet. That's why the whole MI room, it needs to be safeguarded because you have magnetic field within the room. There's another construction, which is a solid core magnet. And this is usually a permanent MI, which is typically low field. And in this construction, you can see that the magnetic field is actually very well maintained. You don't worry so much about the fringe field because your MI is just within that two pole, negative North Pole and the South Pole, and that is usually fine. And usually the magnetic field is vertical. There are all kinds of factors that actually make your superconducting MI scanner very expensive. For example, your field strength, your temporal stability, and your field homogeneity. So this shows a typical superconducting MI, which we typically all use this because we need to have this very high field strength. And you can see that this magnet is actually wired a little bit weirdly. You have a few different sections, which is to make this field as homogeneous as possible, as well as to minimize your fringe field. So these are all electrical wires. But electrical wires will lose power over time, right? So, but in here, all the scanners in CTRIM, it's using the so-called superconducting magnet winding. And all these wires, electrical wires, are actually bathed in liquid helium, which is cooled at 4 degrees Celsius. So it's a very, very low temperature. And if you look at this constructing, that's like almost 90% of your MI scanner. You have your castings and your outer vacuum shield and your shim coils, your main weldings, and these coils. And then you have your heliums. It's constantly being filled and circulated, and you have your cold head. That's all the purpose is to maintain your magnet, your wires in this superconducting condition. And also, after initially being charged, because of the superconducting property, your MI magnetic field is being maintained. You don't need any more power to maintain it. It's superconducting, it does not lose power, and your magnet is always on. There's no turn on and off buttons. Okay, so now let's talk about your second component, which is the radio frequency coils, which is responsible for transmit and receive signals. So you can see our little picture here. Your radio frequency coils are around sandwiched around in the middle, in the least closest to the person. And typically, it's a body transmit coil that's embedded in the scanner. You don't really see it. And then more often than not, we are actually using the body coil for transmitting. And then for transmitting, it's depositing a lot of RF energy to the person. And then you have your receive-only coils, which are placed much closer to the human body. And these are used to receive the MI signals. Okay, so now let's talk about the gradient coils. So gradient coils, remember you see this colorful coded XYZ gradient. The reason for that is because just very simplistically, if you have a wire, which is clockwise here, and you have another wire with a current that is counterclockwise like that, by varying the electrical field, you are actually producing a magnetic field just from Faraday's law. So the clockwise electricity will produce a magnetic field like this in the blue, and then your counterclockwise wire is going to produce a magnetic field like in the purple line here. When you have these two coils placed close to each other at a certain distance, you're actually producing a linearly varying magnetic field in the middle of it. So that is very important because when you produce this linearly varying magnetic field, remember your Lamo frequency, all these protons are being spinning at, it's dependent on the magnetic field. So your main magnetic field is very important to provide a baseline. But now when you apply this little time varying linear magnetic field, you are producing this linearly varying field, and you are letting these protons being at different spatial locations to be spinning slightly faster or slightly slower because of their spatial localization. That's how you can encode X and Y and Z gradient. And if you remember your construction here, you can see your Z gradient is exactly like that. You have two coils, and then you can provide a linearly varying field along the Z direction. And in your X gradient, see you have, now it looks square, but the concept is the same. You can think of them as a loop coil, and you are producing a linearly varying field in the X axis. Same for Y, you are producing a linearly varying field in the Y direction. So, and of course, outside of this linear varying field, your linearity actually falls off. So that's why you have distortions at the edge of the magnet, because your linearity falls off. So your spatial localizer becomes a little bit off, but typically if you do brain scan, because the brain is small, so you are very good within the linear varying range. But if you do a body scan, especially if your subject is very big, it becomes a different story, right? But of course, imaging is a lot more complicated than this. So you typically excite your spins, and then you place your X and Y and Z gradient. And you don't need to understand this, but just know that they are being turned on and off at different timings to realize your XYZ spatial localization. So at the end of the day, you get a so-called K-space in MI, and then after Fourier transform, you get your MI images. So that's your end image, but that is the signals being acquired. Okay, quickly, let's go to the hazard and why we even talk about this. So the strong magnetic field, the problem is force, right? And your Earth magnetic field is 0.5 Gauss. And your modern scanners, especially the ones that we are used to here, they are 1.5 Teslas and 3 Teslas, or for the animal scanner, it's 9.4 Tesla. So they are extremely strong. 1 Tesla equals 10,000 Gauss. So just think of it. And our MI is 3T, but the animal MI is even more stronger. So what's the matter? So they could induce a Magneto hydrodynamic effect, which are reversible. So if you consider your ECG, wave in a person and you move a person inside the scanner, you will notice this T wave is going to be slightly higher. And this voltage induced is proportional to the field strength. And also how your blood vessel is oriented in the MRI. But there's no evidence that such voltage actually result in an ill effect. Very high field of the order of 450 Teslas are really required for alterations of nerve conduction. So we are way below there. So prolonged, the study have shown that prolonged exposure of both male or female rats up to 9.4 Tesla have no effect on the number of offspring's growth rate, feeding patterns, and all this biochemistry and behavioral development. And prolonged occupational exposure for staff to static magnetic field is unlikely to have an effect. There's no evidence exists to support a cumulative effect over time. So this is pretty safe up to now. But FDA does limit for static field exposure for adult children, infant greater than 1 month. It does limit to 8 Tesla. And neonates and infants less than 1 month is less than 4 Tesla. So that is pretty safe and no ill effect so far. So we talked about fringe field, right? So how safe is safe? As again, I have to emphasize the scanner does not only live within the MRI scanner. So typically this shows a magnetic field, an equal magnetic field. When we constructed the rooms of the scanner, we actually see drawings of like this. And then we need to design the room so that anything within the MI room, it can be higher field strength, but outside of the room, it needs to be safe. So how far from the MI is considered safe? We typically consider this 0.5 millitesla or the 5 Gauss line. So we design our room so that as soon as you step inside the scanner room, it may be more than 5 Gauss, but if you are outside of the MI room, it's all shielded so that it's less than 5 Gauss. It's considered safe. But it does not mean that accident does not happen. This actually, it happens if you Google MI accidents, you are going to see all crazy image. Accidents still happen. And while you would think all the hospital staff are extremely well trained, accidents still happen. So all I can say is be vigilant when you enter the MI room. And surprisingly enough, there are still fatalities in 2021. So there's oxygen cylinder kills South Korean man in MI accident, which happened 2021, October 18th. A 60-year-old man and at a South Korean hospital was killed in MI accident where an oxygen cylinder just got sucked into the scanner room. There's another recent MI fatality in 2018. An Indian man died after being sucked into an MI machine, again carrying an oxygen cylinder. So things happen, and you can Google it. There are probably more information about that. And I just want to let you know how strong this can be. This is a very small oxygen tank. It can crash. So you can imagine what could happen if this is a human head, right? Let me move to the next slide. And other than things metallic that are going to be sucked to the MI, there could also be rotational and translational forces. So here shows a picture. I used to do this experiment with MI fellows or residents when we do MI labs. You can literally have aluminum board, which is not ferromagnetic, but you will feel the force when you are trying to cut through the magnetic field. So, and it also varies from 3 Tesla to 1.5 Tesla. And 3 Tesla, this force is going to be a lot higher. You can see how an aluminum board actually, when it cuts through the field, it just goes down very slowly. And again, you can Google it. So that actually caused another fatality in MI, where a 74-year-old female is for MI scan, and the screening somehow gone through the crack that there's an aneurysm, which is not MI safe. And that actually moved. It did not get sucked into the MI, but just moved when it's inside the scanner, and it caused a hemorrhage, and the patient actually died. So accident does happen, and that is why we need to be very vigilant, and we have site constructions with zonings. So zone 1 and zone 2 are free access. That includes freely access areas or your patient screening preparation areas. But we also have zone 3 and zone 4 that is strictly only screen the personnel should enter. So this shows a layout just to show you what are the constructions. So the MI scanner room, it's actually a very well shielded room. That's why the door is so heavy, and it's also guarded by a code. So that is zone 4, which is strictly forbidden for people to enter unless you are trained or you are screened. And zone 3 is our control room where the technologist sits, and also the computer rooms in the back. So that room is supposedly safe to be outside of the 5 Gauss line, but we still require patients, before they are brought into the control room, they should be screened. And of course, all other areas are considered zone 2, which is supposed to be around you do your preparations, patient go to bathrooms, change, and they do their questionnaires. And just to emphasize a little bit more about ferromagnetic or metallic materials, iron, steel, cobalt, nickel alloys are ferromagnetic materials. They get strongly magnetized in the external magnetic field. And the resulting force is proportional to the volume of the ferromagnetic material and the local magnetic field, and then the gradient field. You don't need to remember this equation, but you need to know that the bigger the thing is, and also the stronger the magnetic field is, the force is going to be very high. And an oxygen tank, if it gets sucked into the MI, human force will not be enough to remove it. We literally will need to ramp down the magnet to 1.5 Tesla or 1 Tesla or even lower to remove something. So it's just that strong. And ferromagnetic object should be restricted from entering this field. And sorry. So we have a handheld magnet, And if you are unsure, you can come to see us, and you can use the handheld magnet to test if there's any magnet there. So you should always investigate and document device compatibility and safety informations. And again, sometimes there are things, especially in patients' hair. There may be small beads in the hair, or there may be even hair gels that may be metallic. And they may even pass through your handheld magnet, but they may cause artifact in your image. So that's also something that you don't want. So again, something that you don't want to bring. My advice is just don't bring anything. Make sure that your empty pocket, you don't have anything on you. But other than that, the keys, watches, phones, credit cards is not going to fly, but they are going to be erased. So this is our eligibility checklist. If you don't have it, you should contact us and to get a copy of that. And you should go through your checklist before your patient come to us for scanning. Really, you should do that when you do your consenting form, because if they are not going to be eligible for MI, and that makes zero sense to bring them and enroll them for the MI study, right? And you should call us if there are any concerns that anything checked on the no. And you should really ask every single question, and don't just say, okay, that's no for everything. That's not really working. Here is a quick summary for checklist. So for preliminary screening on any implanted devices, and typically knee and hip replacements are okay. And other devices you should check with us. And absolutely not criteria, no pacemakers, no cochlear implants, no stents of unknown type, especially if they are placed less than 6 weeks. No severe claustrophobia because the person is going to freak out and not wanting to continue inside the MI ball. And also, we need to check if there are any prior eye injuries or foreign bodies. We've literally have turned away people that because they have had a metal work or they have had been in military that they are not sure if there are bullets in their eyes. They have to have prior x-ray to confirm the clearance of metals. A doctor's note confirming the object have been removed because it's dangerous. The metal could move inside the MI. It could blind the person, or it could even kill the person. So even if the person have had a prior MIs at another institute, it does not automatically qualify them, because it may be a lower field strength or if it may be something else. So we will turn them away if they don't have a doctor's note. And also circle contact lenses or those color contact lenses are not MI safe. The person needs to remove them because that's removable, right? And also, just again, like hair gels and anything, ask them not to do any hair work before their MI. For devices, there are typically 3 kinds of device. There may be MI safe, that is non-metallic, plastic, totally pure, 100% plastic, or there may be non-MI safe, the whole list of ferromagnetic items, not MI safe. And there are a whole range of devices that are actually MI conditional. So these becomes a tricky question. So, and there are new medical devices constantly being introduced to MI. So you have to be vigilant in your screening practice, right? And for any implant, you need to check with us. And for implant, more specifically, we will require make and a model, not just, okay, I have this or stent or have something, because we have to have make and a model to establish safety. It can be from even an implant card, any implant, the person will have an implant card for device information. If the person does not have their surgical card, these surgical notes or this implant card, then the coordinator should find the patient charts, and they should contact the patients, either ask the patient to contact themselves to get that information, or you can contact, if you are authorized to do so, to get the device make and model information. I cannot stress more importantly, because we have turned away patients when they come here, they have had some kind of implant, but we cannot know what's the make and model, because we have to turn them away, because we will not be able to scan them, because some of them may be okay, but some of them may not be okay. And especially most people here, you are doing research study. If it's a clinical study, there are risk, there is a benefit risk assessment. And a lot of times devices are considered safe enough for the clinical benefit, but for research study, there is no benefit to the patient. So we cannot assume, or we cannot assume any risk, right? Does that make sense? Okay, we talked so much about that, but now let's move on to IVE pulses and IVE coils and IVE pulses, which the fact is mostly heating. So we talked about coils, IVE coils, which is used for transmit and receive signals, right? So when you do any MI sequence, you start with an IVE pulses, radio frequency pulses. And the radio frequency pulse, they are tuned to the Lamo frequency. Remember, at 3 Tesla, it's 128 megahertz, which is about your radio frequency. So that's why we call the radio frequency pulses. And when they do that, they need to excite the spins, and then they need to excite all these spins, which is originally aligned along the main magnetic field. We need to excite them to the transverse magnetization. And at that time, we can receive signals. So this is your MI signal here. And then I have to strengthen that the problem is a lot of energy. IVE energy is going to deposit to tip these protons to the transverse plane. And the bigger the person, the more protons within the person, the more IVE energy is going to be deposited. And your IVE pulses, there are some heat-sensitive tissues like eyes, testes, and there have been no evidence of ill effect yet. And also your time-varying radio frequency magnetic field, and they can cause heating effect in these electrically conductive materials like leads, wires, implants. So monitoring leads can cause skin burns, and these looped wires or conductive materials can cause induced electric voltage and currents. They can cause heating and displacement. And the clothes that may contain electrically conductive materials. So that's again for implants, other than if it's going to suck, and you can also cause heating in the person. So also skin staples and superficial metallic sutures, if they are not MI safe, they can cause burns. So here are the example of burns. This is a first-degree tattoo burn, which is caused by the metallic ink. And this is I've burned from non-carbon electrodes. And nowadays, the MI-related fatalities are actually a lot less because people are much better trained. but still 70% of reported MR-related injuries are burns. So to characterize this burn, there's something called SAR, specific absorption rate. And for all practical purpose, your SAR is proportional to your main magnetic field squared, and the flip angle in your pulse sequences squared, and inverse proportional to TR and weight. And so there's a lot of things that that you can manipulate. So there are some pulse sequences, imaging method that's more SAR intensive. There are some that's less SAR intensive. Just know that it varies across person to person, as well as sequence to sequence, that the heating will be different. And a little bit more about this electrical current that's being induced in these conductive materials or wires. So we need to have no unnecessary wires left in the room. And we need to be careful with wires and nodes touching the subject's skin. And also just no loops, right? You don't want the person's feet causing a loop or themselves, because human body is a conductive material, right? So you don't want them to make loops. So the wires, if you have to leave something there, don't make the wires in the loop, just make them like zigzagged. And for the person, you don't want them to create loops within their human body. That could also cause local burns. What do we do with tattoos? As I said, there could be metallic ink. Sometimes you can observe there is massive tattoos that have metallic ink, and especially those seem to be metallic. And maybe if it's excessive tattoos, you really don't want to do it. But small tattoos are usually fine. We typically, what we do is we will do it, but we will ask the person to let us know if they feel pain or heating on the body, and then we will immediately stop. And MI safety wires or leads are allowed, but otherwise nothing else is allowed. Okay, now we are going to our third component as well as our third hazard, which is the gradient field, namely the fast switching gradient field. It could cause peripheral nerve stimulation as well as loud noises. So here it shows, again, a picture shows the gradient coils. And if you remember, your magnet is outside, and usually your IF coils is most closer to the human body. And the gradient coils are sandwiched in between. Then you can see some examples of the construction of your gradient coils in real life. And then, as I said, so gradient coils versus the so-called DBDT. So per Faraday's law of induction, rapidly switching of gradient induce electrical currents in conducting tissues. And if you do probably an elementary school experiment, when you make a wire there and then you move an magnet and move it, and then you'll see the light come up. That's how how magnetic field can create electricity, right? So scanners with EPI capacity could have ability to generate currents that may exceed the nerve depolarization threshold and can cause peripheral nerve stimulation. And theoretically, the possibility also exists for stimulating cardiac muscles. And then the so-called DBDT, it's really about, when we talk about switching field, it's like how fast the magnetic field is switched over time, right? The magnetic field is B, so the dB is the change of magnetic field and dt is the change of time. So it's the slope that matters. So when your gradient, it's magnetic field is fastly switching in your pulse sequences, you cause this stimulation. So here shows an example. So the first level is the peripheral nerve stimulation. And then you can have a level 1 peripheral nerve stimulation. And then your cardiac stimulation is way above there. So you may have motor nerves and skeletal muscles that you may feel. And your subject, we've had a subject experiencing their twitching of their nerves on their hand when going through some scans. That's all normal. And also there are some subjects may experience harmless sensation of flashes of light. That's from retinal stimulation. That's also fine, no ill effect. And the respiratory or cardiac stimulation will require exposure levels of order 3 to 80 times more. So that is actually forbidden on the scan. You cannot even reach that. Okay, so now we move on to the noises. So here is a table just shows environmental noise. You can see your whisper in your quiet library is probably 30 dB, and your level at which sustained exposure may result in hearing loss, maybe at 90 to 95 dB. And even short-term exposure can cause permanent damage. That's loudest recommended exposure with hearing protection is 140 dB. So our EPI sequence, the noise level, the echoplanar imaging, like when you do functional MIs and DTIs, these noises potentially can get to that level. So that's pretty loud in the MI scanner. And you can see that, so this gradient strength, a switching noise, the system manufacturer actually must issue a warning on system console if a particular pulse sequence is likely to be over 99 dB. And the acoustic noise in some EPI scans can really reach 140 dBs. But for a matter of fact, our current Prisma scanner, as well as the Biograph, as well as the 9.4 Tesla scanners, they are actually doing a much better job than 10 years ago, the older scanners. The new scanners are a lot quieter. So, but still, you need to use hearing protections. Subjects will have two options. They can do earplugs, which typically offers 10 to 30 dB attenuation. They can do headphones. Again, that's about 10 to 30 dB attenuation. And if possible, you can use both. Someone is especially sensitive, so they can use earplugs as well as a headphone. And also, for all patients or staff remaining in Zoom 4, if they have to be there for whatever reason, either monitoring scan, doing some intervention, or they need to be there as comfort for their kid or their subject, they all need to wear hearing protections because they are going to be exposed to the scanner noise as well. Not as loud as inside the scanner ball, but also quite loud. Okay, so we've gone through all the MI components and their health, their hazards. So now let's go to our MI safety guidelines and mostly what we do at CTRIM. So screening is very important for all non-MI healthcare workers. So for all MI personnel, you guys, if you've gone through the training, you are considered MI personnel. You are trained and educated in MI safety. So you can enter into and work within Zoom 4, the scanner room, independently. But you should really have a MI safety screening checklist done with us. You can come down to see one of our staff here and do a checklist with them to make sure that you are safe yourself, like you don't have any implant in you or anything that forbid you to go inside the scanner room. Or if there's any status change, you should alert us or alert yourself, really. And you should also be very vigilant working around the MI area, and don't let other people to go inside the scanner room unguarded or unauthorized and unscreened. For all non-MI personnel, they must first pass an MI safety screening process before entering Zoom 3. And for example, janitor staff and construction workers, student participants, or visitors, or anybody, if you are accompanying them to our scanner area, you need to be the MI safety officer and MI safety guard to guard them, to make sure that they are safe. They don't put danger to themselves as well as to other people. So the MI safety screening procedure typically are 3 steps. There is written screening form. Which should be done when you screening your subject and get the forms filled. And when they arrive to CTRIM, we will verbally screen them again. Actually, that's the third step. So you should verbally screen them when you do interviews. That's also fine, but they should have a form finished. But then when they come to us, we will verify and go through the checklist again. We have been asked that why do they need to do the MI checklist, since we are going to go through it anyway. But you should know that the reason is because you want to screen them ahead of time and catch any problem way ahead of time. And then we can work out solutions before you bring the person to us, which will be a waste of your energy and our time as well as scanner time. So for pregnant women, if they are healthcare workers, there's actually no current limit to work in and around MI scanners. So if the staff is pregnant, they can still work without any problem. But the guidance is they are not to remain within Zoom 4, the scanner room, during actual scanning. And for patient or for subject, it's typically an exclusion criteria for your research studies. For pediatric patient, we require no toys or non-screened comforter items to enter Zoom 4. All children need to be gowned before entering Zoom 4, and all accompanying or remaining adults should be screened to enter Zoom 3 and Zoom 4 and offer hearing protection. And at CTRIM, if you are here, the subject is going for an MI exam, they all need to exchange their clothes to a gown, because we literally, in all early days, we've had a subject, they said they removed everything whatsoever, but then during the scan, they say, oops, I feel heating in my pocket, I left my phone there. And that actually killed the speaker of the phone, and surprisingly, the phone is still fine. But you don't want that. Okay, so that's pretty much it in terms of the regular procedures. Now it's more or less about emergencies or some occasional things that you are going to do. So for example, if you are the last person to leave the scanner area for whatever reason, and in the MRI room, you want to use disinfection wipes to clean the coils, the MRI table. You want to remove all coils on the table except the spine coil. You want to turn off the MRI scanner door. That's actually not turn off the MRI scanner. It should be the turn off the MRI scanner door. And you want to lock the MRI scanner door, and you want to turn off the lights. Okay, magnet quench. I don't know whether you've heard about it, but it's something called, there is something that you can turn off the MRI room, MRI magnetic field, and it's called quench. So again, magnet is always on, as I've already explained, but it can be powered off. It can be done in a very costly way, and that should only be done when there is personnel injury emergencies. So this is a console that you are going to, you see it around the MRI console room on the wall, you will see that. And that button is the MRI quench button. And it's typically be safeguarded with a plastic guard for a good reason, so that you don't accidentally press it. And once upon a time, it's probably in our old console that Rao used to write this on that box. It's 80,000 quench. Now there's inflation, maybe it's already been $100,000 quench. So that's a very costly thing. So it's a magnet quench. When that happens, the temperature of the superconducting wires will rise very rapidly. And the liquid helium, which is used to cool the superconducting wires, will boil off very violently. And there will be enormous amount of gas vented out of the magnet through a quench vent pipe, and causing large booming sound. And if the quench vent pipe fails, for example, there's ice blockage or a bird decides to make a nest there, the gas will enter the scanner suite. This liquid oxygen will result from supercool air and will increase fire hazard. And the oxygen, when it gets cooled, it will also be hazard to inhale. So this shows an example of quench, a controlled quench. Oops. Oh, codec unavailable. So it actually gives a booming sound. Let's see if this one plays. Oh, sorry. This does not play, but it will be a boom sound, and then you will see all the smoke coming off, and it's like a bomb is going off. Well, this is the picture. So this is the quench happens, and then from the vent pipe, and you see all these liquid helium is getting boiled off. And if a magnet quench happens, there will be rapid reduction of magnetic field in about 2 minutes. And you're going to hear very loud noise and hissing sound. And you need to evacuate Zoom 4 quickly. And you need to close the scanner room door. And there should be no responding fire or rescue personnel allowed in Zoom 3 or Zoom 4 until it's confirmed that the field have successfully been dissipated. So if it is not patient safety, but equipment got sucked to the magnet room, you do not need to quench. There is a much more graceful way to make the field go down, which is called ramp down the magnet. So a service engineer can come out and then gradually reduce the field and increase the temperature of the valves and gradually reduce the magnetic field. So that's much more controlled, and it doesn't create a hardware problem and doesn't create danger. So don't do that if it's just equipment. Okay, there's another button on the in the control room on the wall, which is called emergency power off. And again, that is also safeguarded by a plastic cover. And that is a button that if you go to any of the scanner room here, you're going to see it. And the emergency power off button will shut all power supplies to the scanner, all electronic related. So you are going to shut the power to your scanner console room, and you are going to shut power to the back door, the cabinet, which generate power to the gradients and the IF and everything. But it's not quench, so the magnetic field is still present. So your main magnetic field is an independent piece. It cannot be powered off. But here, the emergency power off button is to power off all the peripheral equipment. So that should be used when there is a hazard for fire, or there is a water leak or potential or other potential hazardous situations. You can press that button to power off. That is usually fine, not very bad to the machine. Okay, so recap in terms of any emergency. The first thing is always to stop scan. You want to remove patient or participant or animals from your MRI room, and you quench the magnet only if patient or participant in danger. And I doubt you need to quench the magnet if it's an animal. That's probably not worth it. But then you want to emergency shut down the magnet in case of fire, water, or other hazardous situation. And then you want to lock the MRI scanner door and keep it closed. And now our doors are all keypad access, so that's actually a lot better. And then you want to evacuate. Okay, so we are done. It's pretty good. So as a summary, MRI environment can be very dangerous. There are static magnetic field like force missile effect, and there are time varying radio frequency magnetic field, which is mostly thermal effect. And you have time varying gradient magnetic field, which is nerve stimulation and a noise. And we should follow strict MRI zoning guidelines, restricted access to Zoom 3 and Zoom 4. And we should have an MRI screening checklist done for all the participants, and never bring anyone to the magnet room unless they have been cleared by an MRI technologist. And also never bring any equipment device into the MRI room unless you have consulted with us. Okay, that's all. Let me leave it at the last page. Our CTRIM director is Rao Gulapalli. Our medical director is Linda Chen. And I'm mostly the physicist, and our technologist is Andy, Jose, Terrence, Rosie. I know this is mostly the human side. The animal side is Sue, and Josh, and Xin Li. And our office administrator is Emily Moore. So now let me turn to you guys. Do you guys have any questions? I've literally have been gone through and I did not stop once for questions. So do you guys have any questions? No question? You can just speak. We don't have too many people here. Okay. Let me stop